Good afternoon. My name is Mahendra Pakala. I'm from Applied Materials. I'll be talking about scaling of new persistent memory. For introduction, I'll cover briefly the status of different memory in market and also their characteristics. Then I'll jump into various scaling challenges in terms of materials and process for MRAM as well as Crosspoint based on PCRAM. So there are many new approaches for the persistent memory that you can find in the literature. Here, I try to show what technology are in manufacturing and sampling stage versus the ones that are in the R&D stage. On the rightmost column, we have the PCRAM based Crosspoint, and that is in the highest density at 128 gigabit per chip. On the leftmost column is MRAM with modest densities up to gigabit. That's also in production for some time now. In terms of wafer fab equipment used to process these materials, PVD or physical wafer deposition tool is the deposition method of choice. For etch process, both reactive ion etch or RIE and ion beam etch or IBE are in the running. These are the areas that Applied has products that enable high volume manufacturing. The rest of the talk, I'll focus primarily on MRAM and phase change memory. On this slide, I plotted the characteristics of Crosspoint, aka 3D Crosspoint and MRAM relative to other commercial or conventional memories. In the three-axis plot, there's the density along one axis, then performance in terms of access time and along the second axis, and endurance on the third axis. I have not plotted the energy, but roughly the non-volatile or persistent memory have higher active power but lower leakage compared to volatile memory. The yellow sun represents the universal memory, which has the best properties in these three metrics, which is still a dream. Start with the 3D NAND, which has the highest density relative to other memories, but the performance and endurance are relatively lower. So that comes on the bottom corner. With 3D Crosspoint, you gain performance and endurance with respect to 3D NAND. This nicely fits in the storage hierarchy above the 3D NAND layer and is what is commonly called persistent memory. At diagonally opposite corner, we have SRAM, which is volatile and more of a working memory, but it is informative to compare along with DRAM and 3D NAND group because that comprises the other extreme of this cube. Both DRAM and SRAM have unlimited endurance, with DRAM sacrificing performance for density. Then if you add in STT-MRAM, it shows up closer to that corner with density less than 3D Crosspoint, but with better performance and endurance expected. So they do have different application space based on their characteristics. Now I'll jump into the fabrication part and scaling challenges for MRAM. MRAM cell is typically one transistor and one resistor. That's 1T1R. So you can use standard transistor from foundries and build up to M4 and M5 level, at which point the MTJ or the R part comes in, and that's we fabricated at Applied Fab. In particular, looking at the materials and processes to reduce switching current and improve MGO dielectric breakdown, and also to look at the impact of the etch and encapsulation process that gives low damage and redeposition. For the magnetic tunneling junction, the deposition of films, including the MGO layer, is done on our Endura Clover system. The system can deposit to more than 10 materials and to form magnetic tunneling junction stacks that are more than 20 layers. This is done with atomic level thickness control and with onboard metrology to control and monitor the process. Using this Endura system, we look at optimizing the process to improve MGO breakdown voltage. One key device parameter is RA, or resistance area product, which exponentially depends on the thickness of the MgO layer. To scale the device voltage, the RA has to be reduced, and this is typically done by reducing effective thickness of MgO layer in the stack. And with that typically reduces the breakdown voltage, since now you have a thinner MgO film. The current products are in the range of RA 5 to 10, and that's about 10 angstrom of MgO layer thickness. We have optimized the barrier process so we can get higher breakdown voltage of about 100 or 1300 millivolts, even at the thinner MgO layer needed to get to the lower RA. This improvement in breakdown is also estimated to improve endurance by about 2 orders. For MRAM, the pitch or cell size scaling is another aspect of development. Usually it is a trilemma. We have to optimize between reducing the redeposition of material on the sidewall, reducing the chemical damage, and thirdly, to improve the pillar profile. Our internal results shown here shows that we can get practically redep-free and undamaged bits for pitches of 130 nanometer or above. Current development effort is focusing on improving yield at sub 100 nanometer pitch needed to scale to N+2 generations. Beyond MRAM, which is the current embodiment of MRAM, which is STT-MRAM, there are additional exciting devices in the broad family of MRAM, including SOT-MRAM and voltage control MRAM. These enable continued scaling of voltage and in terms of energy and also performance. For current STT-MRAM, feasibility to reduce the current to less than 10 microamp has been demonstrated with our industrial partner. SOT-MRAM has advantage of decoupling the endurance and the write performance. By using separate write path, we can achieve less than 5 nanosecond access without compromising endurance. Beyond that, there is the voltage control MRAM. And the advantage of this device is that the energy we obtain, the energy we need to switch is the lowest among all the 3 varieties. And this is due to the fact that BCMA devices are switched by voltage rather than current that's used to switch for STT-MRAM or for SOT-MRAM. However, there are a lot of materials and integration challenges for these 2 new memories in the MRAM family, and these are listed below in the bottom row. Next, I'll talk about phase change memory used as a cross-point architecture. Similar to MRAM, there are material challenges in terms of reducing programming current and reducing damage to cell while patterning using etch. The phase change memory is deposited using Endura impulse system. Again, we can deposit full stack under vacuum with tight composition control. And then the onboard metrology is also enabled on the system to control the film thickness. The phase change memory is usually a chalcogenide with multi-elements, so getting the composition right on the films is key. However, there are some disadvantages for the phase change memory that we need to further improve on. The conventional phase change memory is based on bulk materials, which transforms from crystalline phase to amorphous phase and then back again. The physics of crystallization dictates a longer time for crystallization than amorphization, and also one ends up with a slow set time and high current for reset. To improve performance and symmetric nature, Interface, phase change memory are in development stage. Here, the transformation or phase change happens only at the interface. And because faster transformation happens at the interface, you can get significantly faster performance and lower currents. This is still in CNF stage, and we are optimizing Enduro system to get the right interface structures. The other part of the cross-point cell is a selector, which is also another complex chalcogenide. The Enduro system is also used to deposit this layer, as shown in the picture on the left. One of the key characteristics of this film is to have a low off current so that the overall parasitic current can be reduced in the array. This off current depends not only on the composition of the OTS layer, but also the deposition condition. As shown in the table on the right, we can use our internal test chip to optimize the deposition condition to get to low off current for the selector. In terms of controlling the thickness of the films for the various new memory, Applied has introduced the onboard metrology system that I alluded to in the previous slides. This slide shows some details of the OBM system called TrueFilm OBM. It is integrated into the Endura system and is capable of sub-angstrom resolution to determine film thickness. Besides the material in the cell itself, the metallization is another area that needs to scale. In this slide, we show one of the areas that Applied is developing solution for, which is the low resistive metallization scheme for bitline and wordline. For the current products, you can see that as you go across the word line, the cell at the beginning of the word line sees a different max current than the cell at the end of the word line due to the IR drop. So we are looking at additional low resistive material to reduce this drop. Also, as the dimension scales, doing gap fill between the metal line becomes challenging using conventional dielectric fill. Applied has developed new flowable dielectrics at low temperature that can not only fill the gaps between word line and bit line, but it is also compatible with the subsequent CMP process. This gets to my final slide. The message I want to leave the audience with is that there is a development happening to enable scaling path for next 2 generation for these 2 new technologies. And Applied is providing solutions to make the scaling happen. Thank you, and thanks for your attention.